Hello everyone, my name is Yiyang. What I want to talk about today is the number of faults helpful for cross-company defect prediction. In order to fully discuss this issue, I will introduce my paper from 5 parts. The first part is why I do this work. The second part is the related work in this area. The third part introduces our approach. The fourth part is the introduction of the experiment. The fifth part is the experimental conclusion and their future work. The first is why we do this work. Software defect prediction is one of the most important software quality assurance techniques. Recent years, there have sprung up a large number of excellent articles to solve the cross-company defect prediction problem. However, all of these models are not considered the number of faults whether has an impact on the forecast results. That is to say, the information about the number of faults has not been fully utilized. There are two practical implications for considering the number of defects in cross-company defect prediction. The first, when two source instance has the same distance with the target instance. Considering the number of defects allows the instance with more defects play a greater role in the prediction progress. Second, when we deal with some unbalanced class datasets, a large number of non-defective assimilation. A large number of non-defective instance weight assimilation welded to the defective instance weights have a little impact on the final result. Considering the number of defects will effectively eliminate the impact of a large number of non-defective instance weight assimilation. Part 2. This part we will introduce some related work in defect prediction area. In the early days of defect prediction, people tried to improve the performance of some machine learning algorithm to achieve better predictive results. However, with the evolution of the algorithm, it has been found that it's more difficult to improve the prediction accuracy only by improving the algorithm. So people began to improve the prediction algorithm by using more appropriate training data. Turhan used the nearest neighbor filter model to select the similar data from the source data or the training data for more accurate forecast. INMA select other source data or the training data, but it waits to them to build a transfer naive model. According to selecting the appropriate training data, people also saw that by selecting the valuable characteristics to improve the accuracy of prediction. Zhou Xu proposed a model to sorting the attributes according to the amount of information of them, and then remove the redundant attributes through the clustering to get the most valuable attributes. Part 3. In this section, we present a transfer learning based model considering the number of defects information for cross-company defect prediction. The method consists of 5 major stages. Step 1. Mark how many defects each cross-company instance has. Step 2. Extract the measurement attributes of the instance according to the experiments. Step 3. Weighting the instance. In this stage, we not only considering the similarity between the instances, but also considering the number of defects to get the final weights. Step 4. To based on weighted cross-company instance sets to construct a base defect prediction model. Step 5. According to Bayes defect prediction model to predict whether the project instance is flawed. Next, we will explain the third step, the fourth step, and the fifth step in detail. In the third step, we intend to calculate the weight of the cross-company instance by considering the number of faults and the distance between cross-company instance and the test instance. First, we measure the distance between instances by transfer learning. One of its important principle is the higher the similarity between the cross-company instance and the test instance, the greater the weight. So, in order to determine the weights, we first have to calculate the distance between instances. According to TNB, the distance between instances is measured as follows: find the range of values for each attribute in test set and judge whether each attribute in cross-company instance is within the corresponding attribute range. If yes, the similarity factor of this instance plus 1. Next, we will calculate the weights of each training instance by the above support factors. Here, according to Li Peng's paper, we use the gravitational formula to simulate the gravitational force between the data. That is the weight. In this formula, Wi is the weight of each training instance. G is the universal gravitational constant. Me and Mr is the mass of two objects. R is the distance between the two objects. K is the number of attributes. M is the number of test cases. M is the mass of each attribute. So KMM is the mass of all test cases. SI is the support factor of each training instance. So SIM is the mass of each training instance. Similarly, K 减 SI 加 1 is the distance plus 1 is the distance between each training instance and the test set. In this progress, we can remove some fixed constants and thus get the right part of this formula. In the end, we can get the final weight by assimilating each training instance with. But that's not our final weight. Sometimes when we deal with some problems with imbalanced class, directly using the value calculated above may lead to errors because a large number of non-defective instances with assimilation will lead to the defective instance, which has a little impact on the final result. Considering the number of defects will effectively eliminated the impact of a large number of non-defective instance weight assimilation. So when considering the number of defects information in calculate the weight of each instance, that is to say we add the number of defects on the basis of a formula before. In this, Ni is the number of defects for the ith training instance. Next, we will discuss how to build the Bayes defect prediction model on the basis of this weighted instance. Step 4. In the first step, we use the Bayes classifier or forecasting model on the weighted instance. According to Bayes, in order to calculate the probability of whether X is defective or undefective, we need to calculate the probabilities of whether defective or without defects. and the conditional probability of each attribute in defective or without defects, and consider the normalized evidence of test instance Px. To better explanation, we define the indicative function fxy. If x equal to y, then fxy is e, otherwise fxy is 0. The prior probabilities of defective or without defective can be expressed as this. In this formula, n is the total number of training instances. Ci is the category of the ith training instance. C is the label of the attributes that we want to calculate the prior probabilities. Wi is the weight of the ith training instance, and nc is the total number of categories. Next, we will calculate the conditional probabilities of the jth attribute aj in the training instance. According to, we can see this formula. In this formula, n is the total number of training instances. Aij is the value of jth attributes in ith training instance. Ci is the category of the ith training instance. C is the label of attributes that we want to calculate the conditional probabilities. Wi is the weight of the ith training instance, and nj is the number of different values for attributes aj in the training set. Next, we calculate the normalized evidence of test instance by this formula. In this formula, nc is the total number of categories, k is the number of attributes in instance. PC is introduced in step E, and Paj in Cj. Paj in Ci is introduced in step R. In the fifth step, we predict whether the project instance is flawed according to the base defect prediction model. The probability of whether X is probability of whether X is defective can be calculated by this. In this formula, we can see that PC can be calculated by step E. Paj in Ci can be calculated by step R. Pxi can be calculated by step 3. If the probability of X is defective is bigger than X is without defects, then X is defective. Otherwise, X is without defects. Part 4 experiments. In these experiments, we employed 6 available and commonly used software project database with their 26 release, which can be obtained from Pro-Museum. The detail of the dataset is shown in table 1. Where instance represents the number of instance defects represents the total number of faults in the release. Defect represents the percentage of defect per instance, and max is the maximum value of faults. There are the same 20 independent values and 1 independent values in each dataset. One dependent values is the number of faults. 20 independent values are 20 feature metrics, and we combine the different versions of the same project or the dataset and choose 5 from them together or the training set and the remaining 1 or the test set to do the exam. In order to better verify the performance of NTNB algorithm, we use the training set and test set in table 1 to do a set of comparative experiments. We mainly compare the PDPF and F parameters of NTNB, TNB, and NB. This figure shows the scatter plots of PDPF for the 3 CCTP models on 6 databeds. If it has a higher recovery rate PD and less false alarm PF, then the defect model has more points distributed in the lower right corner, which also represents a better performance of the forecasting model. In the field of cross-company defect prediction, many models do not consider the defects numbers information in predicting the result. However, according to our analysis in some imbalance problem, considering the number of defects will effectively eliminate the impact of a large number of non-defective instances with a simulation. To prove this, we conduct a set of comparative experiments on 6 open cross-company datasets. The result shows that considering the number of defects information can effectively avoid some defective instances, is misjudged as non-defective instances, and improve the accuracy of prediction in some unbalanced program. In the following work, we want to find a balance. To avoid defects number information over fitting the forecast result. For example, give one extreme example. There are 100,000 errors for one instance. Then what can we do to avoid is exceeding interpreting the results? In addition, we will apply our model on the social data to further prove its effectiveness and try to apply our model to other areas. My speech is over. Thank you for listening.